All right, so we're kind of jumping around a little bit in chapter 8. We're going to start off with section 3 because, well, there's a lot of the basics for matrices in section 3. We'll go back and pick up 8.1 and we'll deal with 8.4, and we're not going to be dealing with 8.2. At least I don't think we are. We'll see. All right, so matrices are just an array of numbers arranged in rows and columns, and this is actually covered in section 1, but most of the basic stuff for matrices are covered in this section 3 that we're talking about. So when we group numbers together in rows and columns and place them in brackets, we call that a matrix. We can represent a matrix in one of two different ways. A capital letter, and when we say represent, we're talking about naming it. A capital letter such as capital A, B, or C can denote a matrix, or you can use a lowercase letter enclosed in brackets. And here are the two ways to note A. These are two ways to denote matrix A with elements A sub ij. Now, a general element in that matrix is denoted by A sub ij, where I and j are numbers. The number I represents the row that the element is in, and the j represents the column that it's in. So for example, if we had an element A sub 32, it is the element of A, of matrix A, that's located in the third row, second column. Now, you also are going to refer to a matrix by its order, and its order is the number of rows by the number of columns. That's how you're always going to do it, rows versus columns, or rows by columns. So, a matrix of order m by n has m rows and n columns. If m equals n, in other words, we have the same number of rows as we do columns, the matrix is called a square matrix. And there are special things that you can do with square matrices that you can't do with rectangular matrices. So, just to talk a little bit about this, let's let matrix A be this matrix right here, by 3, 2, 0, -4, -5, -1/5. What is the order of A? Now remember, order is rows by columns. Rows go across, columns go up and down. So how many times can we go across? Well, that's 2. And then how many columns, how many times we can go up or down? It's 3. So this is a 2 by 3 matrix. All right, if A equals the elements A sub ij, identify A sub 2, 3 and A sub 1, 2. Now remember, this is the element that is in the second row, third column. Second row, third column is -1/5. This one's in the first row, second column, so that's going to be 2. Remember, across are rows, and up and down are columns. All right, real quick, let's look at this one, another one here. What's the order of A? Well, remember, it's rows by columns, so you're going to have a row 1, 2, 3. So we've got 2. And then we got 1, 2 columns. Sorry, I said 3 and then wrote down 2. You got 1, 2, 3 rows and 2 columns, so you got a 3 by 2 matrices, or matrix. Identify element A12, first row, second column, -2, and A31, third row, first column, that's 1. All right, now two matrices are equal if and only if they have the same order and corresponding elements are equal. So they must have the same order and all the corresponding elements have to be the same value, have to have the same value. For example, if A, and this is kind of a way that we can turn this equality of matrices around, if matrix A and matrix B are equal, but they're equal if and only if x equals 1, y plus 1 equals 5, z equals 3, and 6 equals 6. So we could actually go through and set those equations up. X equals 1, y plus 1 equals 5, so y would have to equal 4, and z would have to equal 3. If those three things are not true, then these two matrices are not equal. Each corresponding element of the two matrices must be equal. So element 1, 1 in the first matrix must be equal to element 1, 1 in the second one. Element 1, 2 must be equal to element 1, 2 in the other matrix. And 2, 1, 2, 1, and 2, 2, 2, 2. Now, we can also add and subtract matrices as long as they are of the same order. Matrices of the same order are adding by adding the elements in the corresponding positions. So the same way we were talking about two matrices being equal, that's also how we're going to end up adding two matrices. If we're adding matrix A plus matrix B, we're going to add the 1, 1 element to the 1, 1 element, and the 1, 2 element to the 1, 2 element, and the 2, 1 element to the 2, 1 element, and the 2, 2 to the 2, 2. So 1 plus negative 1, negative 2 plus 6, 3 plus 0, and 5 plus 4. Then we just add those independent elements, and that's going to give us the new element of the sum of the matrices. So we end up with 1 plus negative 1 gives me 0, negative 2 plus 6 gives me 4, 3 plus 0 gives me 3, 5 plus 4 gives me 9. So my sum, the matrix added to these two matrices added together, gives me the resulting matrix of 0, 4, 3, 9. Now, guess what? You can do the exact same thing with subtraction, except you have to remember that you are subtracting. It's almost like parentheses, guys. It's almost like you're remembering I'm subtracting every element over here. So I'm doing 1 minus a negative 1, negative 2 minus 6, 3 minus 0, 5 minus 4. So you got to hit that minus with every single element going from one to the other. And we get, when you do all that, 2, negative 8, 3, 1. So addition and subtraction of matrices are very, very easy, but the two things that have to be true are they have to be the same order, and you have to keep all the elements corresponding, and that's the only operations that you do. All right, so let's perform the indicated matrix operations here. So if we're going to add these two, we have a 2 by 3 plus a 2 by 3, so the orders work, and that means that we're going to result in a 2 by 3. So I'm going to go ahead and make my matrix big enough. And 0 plus negative 2 gives me negative 2. 5 plus 3 gives me 8. 3 plus 5 also gives me 8. Negative 2 plus 7 gives me 5. 6 plus negative 9 gives me negative 3. Negative 8 plus 6 gives me negative 2. So there is the sum of these two matrices. Now, to find the difference, once again, I'm doing the same thing. I just have to remember that I am definitely subtracting all the elements in that second matrix. So 2 by 2, 2 by 2, my resulting matrix is going to be 2 by 2. So if I have negative 6 minus a negative 5, that's the same thing as adding 5, so I'm going to get negative 1. 7 minus 6 gives me positive 1. 2 minus 0 gives me 2. And negative 3 minus a negative 4, that's the same thing as adding 4, so I'm going to end up with a positive 1. So negative 1, 1, 2, 1. All right, you guys try these two. I want you to pause the video, try to work these two out, see what you come up with, and I'll show you the answer to this in 3, 2, 1. All right, so here are the two answers. Check your work, see that you got it right. Need to ask questions, make sure you ask in class. All right, now a matrix whose elements are equal to 0 is called a zero matrix. So if A is an m by n matrix and 0 is the m by n zero matrix, then A plus 0 equals A. Matrix A plus the 0 matrix equals A. For example, if I have the matrix negative 5, 2, 3, 6, and I add the 0 matrix to it, we're going to get the exact same thing back. So adding the 0 matrix does not change any of the values. The m by n 0 matrix is called the additive identity for m by n matrices. The reason why is because what does an additive identity do from algebra? If you add the identity, you're going to get the exact same thing back. The additive identity for arithmetic is 0. So if you add 0 to any number, you get the same number. Well, it's the same concept here. Now, for any matrix A, the additive inverse of A, written as negative A, is the matrix with the same order as A, such that every element of negative A, of the opposite of A, sorry, of the additive inverse, is the opposite of the corresponding element of A. So all you're doing is, in this case, is you're going to change the sign of every corresponding element. Now, the reason why the additive inverse means that when we add them together, think about back in algebra, when you add the additive inverse, it cancels it out, and you end up with 0 as a solution. Back in algebra, we learned that if we had 5, its additive inverse was negative 5. And if we had negative 5, its additive inverse was 5. Whatever adds to it to make it equal to 0. And the same thing is true of matrices here. So if we add A plus the additive inverse of A, or the opposite of A, we get a 0 matrix. So negative 5 plus 5, 2 plus negative 2, 3 plus negative 3, 6 plus negative 6. You end up with 0, 0, 0, 0, the 0 matrix. Now, guys, the thing is, you're thinking, oh, well, this is really simple. And if you think back, it's very much like algebra. We're getting the basic ideas, the basic rules of addition, subtraction, multiplication, division, all that stuff with matrices for the same reason we did it way back in Algebra 1. Way back in Algebra 1, we learned all these because they are a foundation that we're going to build a mathematical system on. And guys, there are mathematical systems that deal with matrices. If you go into math classes in college, there are 1 or 2 undergraduate courses that specifically, the entire math class deals only with matrices and doing math on those matrices. It's just ways of manipulating these groups of numbers. All right, so here are the properties of matrix addition, and they're very similar for adding real numbers. If we have matrices A, B, and C, and they're all m by n matrices, and 0 is the m by n 0 matrix, then the following properties are true. Most of these we've already talked about. But a lot of these we're going to recognize from Algebra 1. Matrix A plus matrix B equals matrix B plus matrix A. That's the commutative property. It doesn't matter what way we add matrices, we're going to get the same thing. Same thing with the associative property and the additive identity property and the additive inverse property, which is what we just talked about. So all these are going to hold true. They're properties that hold true for matrices. Now, scalar multiplication, if we have matrix A, and it's a matrix of order m by n, and C is a scalar, that just means a number that's not in the matrix, then the matrix C times A is the m by n matrix given by C times A sub ij. All that means, that's notation, guys, understand this, it's very simple. You're just taking C and multiplying it times every single element in that matrix. That's what this block here says. So this matrix is obtained by multiplying every element of A by the real number C. We call C times matrix A a scalar multiple of matrix A. So if we have matrix A being -1, 4, 3, 0, and matrix B being 2, -3, 5, -6, find the following matrices. If we want to find -5 times B, well, I've got a 2 by 2 here that's B. That's easy to deal with. Actually, that's probably a little bigger than I need. And all we're going to do is we're going to multiply -5 times every element of matrix B. So -5 times 2, -10. -5 times -3, 15. -5 times 5, -25. And -5 times -6, 30. So there is -5 times matrix B. Now this other one over here, we're going to have to do a little bit of more work to. We're going to go ahead and do the 2A and the 3B, then we'll add them together. Guys, don't try to do too many operations in your head and just write down an answer. If you do, you're going to make a mistake. And if you do, on the homework, I'm not going to give you credit for it. You've got to show the steps on how you get your work. So we've got 2 times matrix A. That's once again a 2 by 2. So if I have 2 times this, I'm going to get -2, 8, 6, and 0. And then I'm going to add 3 times matrix B. 3 times this is going to give me 6, -9, 15, -18. All right, and then I can do my addition. Now, you guys are probably wondering, well, why did I have to do the multiplication before I do the addition? Well, you have to because it's order of operations. It still holds true. You have to do the order of operations, as we know, when multiplication comes before addition. So when we go to add this, we got -2 plus 6, which is going to be 4. 8 plus -9, which is -1. 6 plus 15, which is 21. And 0 plus -18, which is -18. So there is my answer of what is 2 times matrix A plus 3 times matrix B. Now, properties of scalar multiplication, if we have matrix A and matrix B, and they are m by n matrices, and C and D are scalars, then the following properties are true. We can multiply C times D and then multiply that times matrix A, or we can multiply the scalar D times A and then multiply that resulting matrix times C. In other words, it doesn't matter how we associate that multiplication. 1 times the matrix, the scalar of 1 times any matrix is just going to be itself. The distributive property, any scalar that you're multiplying times a sum or difference of matrices, you can either do it after you've done the multiplication, or sorry, the addition or subtraction, or you can do it before. It doesn't matter. The distributive property still holds true. And the same is true about the distributive property of scalars with a matrix. So you can distribute the scalar or you can distribute the matrix. Either way, you're going to get the same thing. All right, so if we have 2 times x plus a equals b, we want to find what matrix x is. So we have 2 times x plus a equals b. And if we want to solve for x, before you do anything with the matrices, you can go ahead and rearrange all this stuff. What would we do algebraically to solve for x? You would subtract a from both sides. So you're going to get 2 times matrix x is equal to matrix b minus matrix a. Now, here's the only difference here, and it's not really a difference, but it's a difference in notation. You can't really divide, so what you do is you multiply by 1/2. So I'm going to have that matrix, whatever it might be, and I'm going to multiply it by 1/2. So x is equal to 1/2, that's a scalar, of, and we're going to go ahead and do this, b, negative 6,591, minus matrix A, 1, negative 5, 0, 2. All right, so that's going to be 1/2 times, and when I get my, let me go ahead and get rid of the parentheses here. I get a 4 by 4, or 2 by 2 here. So negative 6 minus 1, negative 7. 5 minus negative 5, that's going to give me 10, because I'm subtracting a negative, same thing as adding a positive. And then 9 minus 0 is 9. 1 minus 2 is negative 1. And then all we're going to do is multiply 1/2 by, and remember, what do we do with 1/2? Multiply it times every single one of these. So we're going to end up with negative 7/2, 5, 9/2, and negative 1/2. So that is matrix. Now, by far, the most difficult thing that most people run into is matrix multiplication. Now, the reason why is because while addition has been very straightforward, addition, subtraction, scalar multiplication has been very straightforward, matrix multiplication is not so much. It's a row by column multiplication. Now, we do not multiply two matrices by multiplying the corresponding entries of the matrices. Instead, we must think of matrix multiplication as row by column multiplication. To better understand how this works, let's begin with a definition of a matrix, of matrix multiplication for matrices of order 2 by 2. So if we are multiplying A times B, and here is matrix A and here is matrix B, here's what we're doing. This is where this stuff over here comes from. We go with row 1 times column 1. And we're going to do A times E plus B times G. And that whole thing right there is my element 1, 1. Now the reason I know it's element 1, 1 is because it comes from the first row, first column. When I go to do my second element there in row 1, I'm going to do row 1, second column. A times F, B times H. And I add those two things together. And you just go through the entire process doing the exact same thing. So when I want to do my second column, or my second row here, I'm going to do CD times EG. There it is, C times E plus D times G. And then that's going to give me my 2, 1 element, my 2, 2 element, second row, second column, C times F plus D times H. So that's a definition of how you do a 2 by 2 multiplication. So let's look at one. Let's find what the product of A times B is if A is 2, 3, 4, 7 and B is 0, 1, 5, 6. So 2, 3, 4, 7 and 0, 1, 5, 6. Now, I'm still going to end up with a 2 by 2, and we'll talk more about that in just a second as to why I know that. But here's the thing. You're going to need more room because you're going to have the sum of these products in every single one of the elements. For instance, if I'm doing my 1 element, I'm doing row 1, column 1, I'm going to do 2 times 0 plus 3 times 5. Row, column. 2 times 0, 3 times 5. All right, and for my 1, 2, row 1, column 2, 2 times 1, 2, plus 3 times 6, 18. Element 2, 1 here, I'm going to do row 2, column 1, 4 times 0, 0, plus 7 times 5, 35. And for my last one, my 2, 2 element, row 2, column 2, 4 times 1, 4, 7 times 6, plus 42. All right, and then when I simplify all that down, I'm going to get 15, 20, 35, 46. And there is the product of matrix A times matrix B. All right, I want you guys to try this. Multiply matrix A times matrix B and see what you come up with. Pause the video, give it a try, and then start the video back and I'll show you the answer in 3, 2, 1. All right, so here's the answer. So check your work. Row, column, 1 times 4, 3 times 1, that's where that comes from. 1 times 6, 3 times 0, that's where that one comes from. 2 times 4, 5 times 1, that's where this comes from. And 2 times 6, 5 times 0, that's where that one comes from. And just do the sums and you get that answer. All right, so the product of an M by N matrix A and an N by P matrix B is an M by P matrix. So we don't have to have two equal dimension or equal order matrices to multiply. And the thing is, they don't have to be square matrices like we've looked at either. So we have an M by N times an N by P, and we end up, resultant matrix is an M by P, whose elements are found as follows, the same way we've been doing in in the previous ones, how I talked about row 1, column 1, row 1, column 2, etc., etc. You're going to do it the exact same way. The only little trick here is this thing down here at the bottom. The following diagram illustrates the first sentence in the box up here, defining matrix multiplication. The diagram is helpful in determining not only the order of the product AB, but can you actually do it? If these two right here are not equal, you cannot multiply the matrices. So for instance, if I have a 2 by 3 matrix and I want to multiply it by a 2 by 3 matrix, it doesn't work. I can't do that because these numbers right here don't match. So not possible. Now, if this was a 3 by 2 matrix, then it does work. It's possible, and not only that, but I'm going to get a 2 by 2 as my resulting matrix. Possible, and answer is a 2 by 2. So that's how you determine A, can you do it, and B, what your resulting matrix is going to be. So the first one, whatever you're multiplying first times second, and here's the thing, with matrices, the commutative property doesn't apply. It has to be, they're going to be different numbers, in different matrices depending on what order you multiply them in. And in some cases, they're not even multipliable in one way, but they will be in the other. Like this one right here. Actually, no, that one will be multipliable both ways. But if this was a 3 by 3 times a 3 by 2, it's multipliable this way, but if you did b times a, it's not multipliable because you do 3 times 2 by 3 by 3, inside numbers don't match, so it's not possible anymore. So commutative property does not apply with multiplying matrices. It does with scalars times matrices, but not with matrices times matrices. All right, matrices A and B are defined as follows. Find each product, if possible, A times B and B times A. So let's do A times B. Well, what do we have here? We have 1 by 3. So for the first one, I'm going to see if it's doable first. And the second one, it's 3 by 1. So those are going to match. But here, what do we end up with? A 1 by 1 matrix. Well, that's easy to deal with. So all I'm going to do is go across my row and down my column. 1 times 4, 4, plus 2 times 5, 10, plus 3 times 6, 18. And then when I add those, 14 plus 18 gives me 32. Do not write that as just a number because it's not just a number. It is a single element matrix with that one element being 32. Don't just write the number 32. It's not the same thing. All right, so let's do B times A now. So B times A, we're going to have, let me change colors here so we don't get them all mixed up. We're going to have 3 by 1 times a 1 by 3. And that means we can do it since the insides match, and we're going to end up with a 3 by 3 matrix. So we're going to need a little more room here, but not too much. And remember, I'm going to go ahead and write it over here just because I'm very spatial and I need to see B times A, not A times B, and try to do it backwards. So row, column, so 4 times 1, 5 times 2, well, no, let me do my process. So this row times every one of these columns, so 4 times 1, 4 times 2, and 4 times 3, and then 5 times 1, 5 times 2, and 5 times 3, and 6 times 1, row times column. So the third row, first column gives me the 3, 1 element. Third row times the second column is going to give me 12, and that gives me the 3, 2 element. And then 6 times 3 gives me 18. So there is my matrices, my matrix right there. So here, this one over here, well, let's do this one since I've already got. So product BA is this 3 by 3 matrix, and product AB is this single element matrix. So hopefully here you can see order does make a very big difference in what your result's going to be, and they're not going to be the same. There are instances where they might be, but it's a special case. It is not the rule. The rule is commutative property does not apply because it would have to apply for everything, and as we can see right here, it does not apply to everything. All right, that's where I'm going to stop. We're going to do a couple of more complicated matrix multiplication problems in class, but that's the basics of it. I mean, it just gets a little more larger and a little more complicated, but as far as the math, it doesn't get any more difficult. There's just more things to keep track of. But we'll look at a couple of examples of those in class.